Okay, we're going to go ahead and continue with the exam review packet, and starting with number 9. Okay, so the first thing that you want to notice here is that there are a few key points that you want to have on your sign chart. If you don't remember what that is, that's where you have important points such as x-intercepts and vertical asymptotes, and you're going to see where it's positive, where it's negative, etc. to answer this question here, where is this function less than 0? So if you notice here, there is a 0 at 0, and I'm going to label it 0, which means that I can include it if I need to. And then 2 is a point of something of undefined. And if I go ahead and pick a test point in this region, such as -1, I'll have a negative number divided by -1 minus -2 is a negative number, which overall gives me a positive number. Something between 0 and 2, like 1, would give me a positive over a negative, which overall would be negative. And then something to the right of 2, both the numerator and denominator would be positive, overall resulting in a positive. Therefore, my answer, if I'm interested in where is this rational function less than 0, okay, well, you can actually just highlight where it's less than 0. It's here, and that's the only part, but you need to be careful and make sure that you're not going to include points where it's undefined, which would be 2. And I'm actually not interested in where it's 0, exactly 0 either, so I'm not going to include 0 or 2 here. So again, just to recap that, 0 and 2 are not included, 2 because it's an asymptote, 0 because I'm not interested in where it's equal to 0, simply where it's less than 0, which is between those two numbers. Okay, the next problem we're going to do is number 10. So again, you can follow along in your exam review packet. So let's set up our sign chart. So first of all, if I factor this guy, I get x plus 5, x plus 2. So there are points of it being undefined at -5 and -2. And let's mark that those are undefined points to be sure not to include them. And then there's also an x-intercept or a 0 at 3. Okay. All right, so let's plug in some points here. So if I plug in a number to the left of -5, like -6, -6 minus 3 is a negative number, -6 plus 5 is a negative number, -6 plus 2 is a negative number, all resulting in negative. Here, if you pick something like -3, -3 minus 3 is negative, -3 plus 5 is positive, -3 plus 2 is negative. Overall, this is positive. Pick a number between -2 and 3, like 0. 0 minus 3 is negative. 0 plus 5 is positive. 0 plus 2 is positive. Overall, this is negative. And pick something to the right of 3, like 4. 4 minus 3 is positive. 4 plus 5 is positive. 4 plus 2 is positive. So overall, this is positive. And so I'm interested in where it's greater than or equal to 0. So that is here. And let me get my highlighter out instead. So it's here and to the right of 3. And because it's greater than or equal to 0, I'm actually going to include the 3 because that's where it's equal to 0. But notice -5 and -2 will never be included because those are asymptotes. So my answer will be between -5 and -2, or to the right, including 3. Okay, so there you have number 10. Let's move on to number 11. So now we're going to start getting into some partial fractions. Okay, so first of all, this guy here can be factored as x minus 2, x minus 3. So I'm actually going to rewrite the problem down here using that factoring. So I have two linear factors in the denominator here. Each of them will get its own constant. Remember, if you have an irreducible quadratic in the bottom, you would get a linear numerator, but since these are both already linear, I get constant numerator. So a over x minus 2 plus b over x minus 3. Now I'm going to multiply both sides to get rid of the denominators. So I just ran out of room there, but these are being multiplied, not divided. So I'm left with 13x minus 31 equals a. Here the x minus 2's cancel, so I'm left with a times x minus 3. The next one, the x minus 3's cancel, so I'm left with b times x minus 2. And we're just going to do some algebra here. Rearrange everything, distribute the a. Remember, a and b are constants. Okay. Rearrange it so I can compare coefficients. Factor out the x. Okay. So here you can see a plus b has to be the coefficient of x. The coefficient of x is 13. Hence, a plus b is equal to 13. And we'll do that on the next page. So we have a plus b is equal to 13. Then if we go back here and compare the constants with the constants, negative 3a minus 2b is equal to negative 31. So that is the other part of our system here. Negative 3a minus 2b is equal to negative 31. So here I'm going to write a equals 13 minus b. There's a few ways you can do this, so this isn't the only way. And take this a and put it in for that a. A little bit nicer. There you go. Distribute the negative 3. So negative 39 plus 3b minus 2b is negative 31. These two combined give me 1b, and I can add 39 to the other side. So b equals 8, which now if I go up here, I have a is 13 minus 8, so a is 5. So my final answer is as follows. 13x minus 31 over x squared minus 5x plus 6. The original problem is equal to a over x minus 2 plus b over x minus 3. Okay, so there you have number 11 from the start to finish. It's kind of a long problem. Let's go on to number 12. So let's go ahead and factor it. X plus 1, x minus 2. And I'm going to write that down here, just rewrite it. So here I also have two linear factors in the bottom, so each of them will get their own constant numerator. Okay. Multiply both sides by x plus 1, x minus 2. I'm left with negative 9 equals a times here the x plus 1s will cancel, so I'm left with a times x minus 2 plus b times x plus 1. Do some algebra. rearrange so the x's are next to each other. And if you can see what it's going to look like in the end, you can skip these steps, but I like to do this just kind of to make sure that I don't miss anything. Okay. So here you can see that the coefficient of x, there's no x's over here, so coefficient of x, a plus b, is equal to 0. Which right away I can say a is equal to negative b. And then I have this constant, negative 2a plus b is equal to negative 9. So negative 2a plus b is equal to negative 9. So if I take this guy and put in for a here, I have negative 2a, which is negative b, plus b equals negative 9. And so you can see b will be negative 3, which in turn means that a is equal to the negative of b, which is 3. So my final answer from the first part of the problem, negative 9 over x squared minus x minus 2 is equal to a over x plus 1 plus b over x minus 2. And you can, if you want, you can write this here as minus 3 if you want, but I just like to keep it separate. So that is my final answer. All right, let's move on to number 13. So this one says, find the following limit. So those of you that are going to take calculus, you will spend about half the time talking about limits. Limits are a big concept in calculus. Okay, at least for the first part of it. All right, so the way I'm going to do this is I'm actually going to graph it. There's a few ways you can do it, but I like to graph it just to have an idea of what's happening with the graph. There's a few other techniques that you'll learn in calculus, but for now that's good enough. So here I'm going to factor everything. So this factors to the following. Okay, so you can see here that these are going to cancel. And so that means that there's going to be a removable discontinuity. Okay. So basing everything off of this function except for that removable discontinuity, you can see there's a vertical asymptote at x equals negative 10. There is a horizontal asymptote of 1 because the degrees here are the same, so I do this coefficient divided by this one. And we can say that there is a removable discontinuity at 2 comma something, the 2 coming from setting this factor equal to 0 and solving. So to find what the something is, treating this as sort of my f of x, if you will, f of 2 is equal to 2 minus 3 over 2 plus 10, which is negative 1/12. Okay. So actually, to save some time, we don't have to graph the entire thing. That was the original approach that I went through when I did this problem originally, but you can also kind of think about it. If you're thinking about a removable discontinuity, by definition what that means is that the limit as you approach 2 here, from the left and right, both approach negative 1/12. So what do I mean by that? It means that in order for it to be a removable discontinuity, this is actually a hole, which means if you were to graph that part, so I guess just a quick sketch here. There's a hole right here at 2 negative 1/12. so that it kind of goes like, again, I'm kind of skipping around here as far as information for the graph is concerned, but it kind of goes like that, right? Where there's a hole there and you can graph the rest of it kind of quickly. We had a vertical asymptote at -10, right? So you have this other part of the graph over here, but really what I care about is as you approach 2, right? If you see the x approaches 2 here, so as I approach 2 from the left, it goes to -1/12. And as I approach it from the right, it also approaches -1/12. So the answer actually would be the limit as x approaches 2, as you can guess now, would be of the function is indeed -1/12, because from the left, and from the right, that's the y value that it approaches. So there is kind of a really, really rough sketch there. Again, you can find this, but the part that we really care about is as you approach 2 from the left and right. So that would be number 13. Okay, so that is the set of problems 9 through 13 from the review packet, and we'll continue with the next session.